All right. Good morning, everybody. Thanks again for coming to the Center for HCI seminar today. Um, Now I think it's time to get started. So let me introduce today's speaker. I'm Dr. Hong Yeo. I'm the Director of Center for Human-Centric Interfaces and Engineering at Georgia Tech. Personally, it's my great pleasure to introduce today's speaker, Dr. Nam. Dr. Nam is an associate professor and Anderson faculty scholar in the Department of Mechanical Science and Engineering at the University of Illinois Urbana-Champaign. He received his PhD in applied physics from Harvard University. Afterward, he worked as a postdoctoral fellow at the University of California, Berkeley. And Dr. Nam is the recipient of many, many awards. The list is super long, so let me just introduce representative awards. He received NSF Career Award, AFOSR and ONR Young Investigator Awards, NASA Early Career Faculty Award, and more. And today he will introduce his research about strain-engineered Van Waals materials for flexible and deformable electronics. So I'm very, very excited to hear his wonderful research works today. So please join me in welcoming Dr. Nam.
Thank you, Professor Yellen, for the kind invitation. It's a different way of meeting these days, but it's a great pleasure to be here and tell you a little bit about what we have been working on in this theme of flexible, deformable electronics. As you see, I think I have to make a statement that this topic of research, in my typical talk, is something that I don't talk too much about. So it's actually the first time I'm presenting this slide set I put together yesterday. So you might hear a bit of it's first for me. And also this Zoom or this BlueJeans platform is also relatively new, though it's pretty similar. Hopefully I'll be able to tell you a little bit about what we're doing, but there are a couple of new kind of things for me. So today I'm going to talk to you about, I think, widely known as 2D materials and how we can use them to either create a new different types of flexible form factor, or we can utilize them to enhance the property or capability of flexible electronics. So that would be kind of the topic of my talk. And before I get started, I just wanted to kind of briefly mention this quad. It looks very quiet and comforting. And we call this quad as the Bardeen quad. If you have ever been to Urbana-Champaign to celebrate John Bardeen's very prominent research, he's one of our faculty who won the Nobel Physics Prize twice, right? As inventor of a transistor back in Bell Lab, and then after that, a theory behind superconductivity, BCS theory, and Bardeen was the main figure that who enabled that with his student and postdoc at Illinois. So we have lots of appreciation for fundamental science in engineering, and that's kind of the spirit, I'll say, of kind of the feature of Illinois engineering. Let me see if I can, it looks like oh, okay. Before a button didn't work for just a little bit. I just wanted to make an acknowledgement of the students who did the work, including the alumni. There are a few of them now in different places. Of course, the work that I'm going to present today are relatively more recent work, so it's from either current students, I put their names and initials down in my slide, or the recent alumni who worked and became independent and working on their own research interest. And I also want to say I have a couple of postdoc openings in my laboratory, so if you see something today that might be of your interest, please let me know. Okay, so let's get started. This is a very kind of the generic slide I show whenever I give a talk, and it really, I think, showcases some of the interesting features that either are engineered or that are existing in nature, right? We see a lot of interesting features. And if you are a mechanical engineer, if some of you are, right, any major, you would love to understand, for example, how these structures are formed, right? What's the mechanics behind it? If you are more of a manufacturing person, you probably think about how can I make them, right? With this precision, with the control in the specific material that you might be using. So something that I thought is interesting, and coming from a material science background, and trying to work with folks in mechanical engineering, I realized that these structures are also a feature perhaps that can be tied to materials property or enable new property due to these structural, right, features that we can define. For example, I think a very good example is shown on the right, this blue helmet. As you can see, it has this cellulose structure, right? It's right. It takes a lot of effort probably to make this, but once you have the structure helmet, it's not only lighter weight, but also can be foldable. At the same time, it delivers similar impact resistance, right? The energy can absorb. That's one of the characteristics as a helmet. And as you can see, you can achieve more or less the same thing, but without this bulk continuous material. And what, if you think about what enabled that, is really this architecture, right, that's built into this material that enable new mechanical properties in this case. So our question that we became interested over the years was, well, can we do the same thing, but control the property that's beyond mechanical property? Can I control optical property? Can I control phonon transport? Can I control electron transport? So right, because it's a similar concept, except for the length scale of these deformations just need to be different because, right, everything has a characteristic length scale. And as long as your feature size start to reach that of those characteristic length scales, you could start to play this, right, structure property relationship, but in a very different way. So that's kind of our interest. And generally, my talk will kind of describe around that kind of concept. Today, I will show you just a little bit, not actually too much, because the focus is a bit more on mechanics side or mechanical features that we can enable in this particular talk. So if I introduce my laboratory in general, we worked on a number of stuff. And I think if I really think about what's the common theme of what all we do is really this materials. So essentially bring in advanced materials and again, start to combine that with mechanics, right? These deformations, whether that's elastic or plastic, and try to combine them or this unique opportunity and create this functionality that's beyond, right, what we know we can control or what's been popular in the community. So that's really kind of the theme that usually, right, I think that we do research around. And we have different thrusts in some sense or the focuses, right, that might include some of the scalability of the structures that we build. And then we have to try to understand properties such as mechanical properties or some of the properties I just discussed beyond mechanical due to the structure formation in a particular material that we're going to work on, and some of the applications towards wearable flexible electronics. So that's kind of the theme, right, that we work on. And we have some collaboration throughout campus or beyond campus that try to right, leverage some of the opportunities and collaborations that are existing. So if I briefly talk about the material that we worked on, it's widely accepted or understood as a 2D material. It's an atomically-thin class of material that exhibits quite interesting properties, of course, dependent on crystal structure, right? As a material scientist, that's kind of the way you think about things. So if you have a different element making the crystal in a certain form, you have a specific properties that the materials exhibit. It turns out the graphene is the most popular material, truly in one atom thick format, right? True 2D crystal. It is a semi-metal. It has a zero band gap, and it's right in an optical. I mean, to our eye, it look like semi-transparent. So it found lots of kind of interesting applications and of course, related to its fundamental properties. But then there are kind of mixed classes of these thin materials. Some of them are not truly a 2D, given that they are more than one atom thick. For example, one of the popular materials, such as moly sulfide, it has a midplane of molybdenum and have a sulfur on top and bottom, so it makes them 3 atom thick crystal. But there's no outer plane bond, so basically it's a layered crystal. So these moly sulfide will stack almost in the same way as graphene stack up to become graphite. But moly sulfide becomes direct optical gap, energy gap semiconductor in a visible spectrum. So it's a pretty interesting material for optoelectronics, as well as there are other more kind of similar and different 2D material. Here I'm showing you black phosphorus. It has a very interesting kind of puckered crystal structure. It also has a specific band gap because of that. And on the very left, you have hexaboronitride. It's same as the graphene's crystal structure, except for you have a boron nitrogen creating the same hexagonal lattice. This is an insulating material. So we basically have a good number of material. Actually, there are a huge number of these materials that we can start to play, right? Start to engineer, except for, right, not every material can be synthesized in a large scale. So we choose to work with some of the material that are much more easier when it comes to engineering applications. So in this particular talk, I'm going to talk a little bit about graphene. I'm going to talk about moly sulfide. I think those are the key material that I'm going to present to you today. Some of the interests as we think about this kind of 2D material and think about some of the features that this material can provide us with. This is one chart I think it's quite interesting, and it kind of puts things in perspective, right, in terms of how the impact of thinness plays in lots of things we do. So if you look at this particular graph, I'm plotting the field effect mobility. So this is, right, carrier velocity, carrier transport in a given electric field of a material. My x-axis is a mechanical bending stiffness, right? How easy to bend a particular material. And so here we kind of look at the material that people have been working on in a right space, research space of nanomaterial in the past decades or more. Here I'm showing you nanowires, nanomembranes, organic semiconductors. Some of them we consider them as very, very soft, right, when it comes to bending, easy to deform. There are many seminal works using such features to create, right, very interesting, delicate kind of pop-up structure using semiconductors, using very thin film. And if you look at the stiffness of these films, of course, these are thickness-dependent property. But if we take about 100 nanometer as our kind of length scale, common length scale for these, we're looking at about a million times stiffer bending stiffness, that, right, as opposed to that of 2D material. Or if you think about a cell membrane, lipid bilayers, we're looking at about, right, 1 to 10 electron volts of our bending stiffness, whereas, right, most of the semiconductors were not really anywhere close to that. It's quite surprising that these 2D materials, just because of their thinness, now it's approaching that of the biological systems when it comes to bending. Of course, still in terms of stretching, it's very, very stiff. So in-plane stretching is very, very difficult, but out-of-plane bending is very, very easy. So the kind of the interesting question then you can ask, right, is that how can we utilize it? Of course, if you're engineering, if you want to use the thin film as is, you would say, how do I make it flat and the flattest possible so that I don't need to worry about any bending deformation that might be present in the system I work on. So that's one strategy, and that's one research theme. But what we did was we asked the opposite question. Because it's so easy to bend and deform, it's super deformable system, as if it's like a cell membrane, can we actually deform it and control such a deformation, and again start to couple that deformation of structure with number of properties in material, such as electron transport, plasmonic features, phonons, excitons. So that's kind of really the engineering aspect or material aspect in the research that we do. And really based on this diminishing bending rigidity argument. And we're having a lot of fun with that. And though, right, if you then ask the question is what can be really practical, right? So there's understanding piece of it. How do we use these types of deformation to control material property? It's a lot of fundamental science, but then the question becomes how do you right, pull that understanding and try to develop a system or devices that could be ever useful. So that's the topic of today's presentation, focusing much more on, okay, we have some control of designs, understanding, are there any interesting features I can extract from that? And I said, this is the part where relatively early, so we're now nowhere close to, right, what Professor Yeo is doing, and lots of folks in flexible electronics community that I'll try to convince you there are some interesting possibilities. So the first kind of topic I would like to discuss is related to deformation. And later on, I'm going to talk a little bit about interfaces as well, because these two turns out to be quite an interesting, has a significant impact in the properties of devices that we're going to look at. So the first example, so it's not really a one-layer thin system in a real life. It has substrates, it has structures around it. So something that we have done relatively recently, about a year ago, or started about a year ago, was to think about, is there a way, right, given that these materials can be easily patterned or can create some deformation easily, is there a way to create a structure that can be practical? So that's how we started this whole investigation, and we learned something new. So that's actually what happened. But here is the device that we built. It's very simple. It's a very thin poly image. It's about 2 to 4 micron thin, right, control with the spin coating. On top and bottom is sandwiched. And then in the middle, you have a graphene pattern exactly the same way as the poly image. So this is kind of the simplest structure that we have built, and you're seeing on the left our image. And as this structure, for some might be familiar, it's basically, right, a structure known as a Kirigami. You start with a thick slab of material, and then you introduce cuts to the material so as to enhance, right, or to enable this stretching ability of this structure, right? Otherwise, it's going to be very, very stiff, right, when it comes to stretching operation. So that's kind of the structure or device that we have built. And I'll talk a little bit about mechanics associated with this. But let me first tell you what we observed. So on a device level, let's see. Okay, so yeah, sorry, let me just move my screen a little bit. So this is kind of the observation we had. It's really nothing kind of quite striking here, but we thought it was very interesting. So what we are doing here on the panel A, I grabbed that Kirigami graphene sandwich, and I'm simply stretching up to 250%. So that's by design. So we created a number of cuts, size of these cuts, width of the cuts, and depth of the cuts, such that it can stretch 250. And this is the result you saw. You can see the change in resistance up to 250 is truly negligible. So it was quite a surprise. We know, right, Kirigami enables mechanical, right, this operation, but by doing this, right, in a way, with graphene, it turns out, right, if you are someone who are familiar with strain gauges, we've created a porous strain gauge in the world. So gauge factor is essentially 0. We're not able to define it. So that's interesting. So let's keep testing, right? So panel B, I'm showing you the turns. So you can grab it, you turn it 1 and 2 turns. So 720, torsional, deformation, same thing. We're not seeing any changes in resistance. There's some fluctuations, but nothing, right, consistently going up or down. And you can do mixed mode, that's our panel C, right? That's a real-time measurement. Whatever you do, right, stretch, twist, quite interesting. And you can, right, ask your student to do some cyclic tests. So right, yeah, lots of time there, but I mean, you start to see something interesting. It looks like the mechanical deformation isn't changing anything in terms of electrical conductivity, conductance in the system. So we call this strain insensitivity. When it comes to strain coupling to electrical properties, it looks as if it's completely decoupled. Although as we know that most of the semiconductors or materials have piezo resistance, and it looks like we're able to completely kind of not seeing that aspect by creating this particular Kirigami structure. So we wanted to understand what's happening really with this Kirigami under this deformation as I talked about. And here I'm showing you just one simulation study that enable us to understand, that we can design these structure with these simulation, but also at the same time help us to predict and also perhaps come up with the explanations of why this strain insensitivity exists in our structure. So here, the upper two rows of the panel, it really shows us that the image that you're showing on top is a side view of this Kirigami. So when you stretch, in order to be able to stretch, it's not only stretching these bridges or these long kind of structure, it also creates the out of plane bending. And that's how it relaxes the local strain and allows not only stretchability, but also minimizing the strain on the structure, on the material itself, which is also positioned in the neutral plane. And of course, you can start asking, well, these bridges are interesting, but if you want to start to add devices in this type of architecture, and then if you think beyond just a simple structure, you need something different. So here in the panel K, we added a middle island. So it's the simplest version we have worked on, and we wanted to put certain device in there, and again test the similar whether the strain insensitivity will be there, and understand what are the local strains with the help of simulation, and also predict what is the stretching limit of this device. So it turns out it's actually very, very easy to predict those. Well, I won't say it's easy, but very predictable, reliable. And we even put out a nano hub as part of our manufacturing hub, nano manufacturing hub at Illinois, a user interface that you can actually go and design and simulate these types of particularly Kirigami structures for free. So if you're interested, you can look for those, and it is quite useful. So we built a bit more device capability in the particular structure, just put a single island. And two examples that we did. It's a very simple example under, again, stretching, even twisting the structure was to ask, well, we can create a field effect transistor at the middle portion that we are interested in pursuing some of the biochemical sensing routes, and then that's showing in panel E. And here I'm showing you just a simple IVG, so source drain current gated by the water gate. So we put a drop of water, and we're gating channel through external wires in this particular setting. And as you can see, as you apply different mechanical deformation, whether you stretch or twist, essentially the IVG curve is exactly the same kind of conceptually the same as our strain gauge type of measurement. And you can repeat the same experiment as a sensor, in this case, a photo sensor that is under different illumination intensity, under different deformation mode, which show really the same kind of responses. So this really was kind of, for us, an interesting observation. Although we didn't start with this anticipation, but it turns out this strain sensitivity is something that could be quite powerful when it comes to trying to decouple any motion artifact. If it was a wearable sensor platform, we run around, we generate these piezo-resistive signals. Of course, sometimes you love that, sometimes you don't like that. So you can do that with signal processing, but you can try to do that with these design component as well. So what we have done more recently was to extend this to something more like a ray concept. So here I'm showing you it's the same process, except for we have more islands connected with these bridges. So it's like a bridge island design, the basic expansion of what we had demonstrated early on. just a bit more fabrication, more integration here. And here's one example. It's a 2x2 Kirigami. And in each island, you can put a number of different things, whether that's graphene FET, and you can modify the surface as a glucose sensor channel, in typical resistance temperature gauge, and a pH sensor. So here I'm just showing you a movie of, right, it's much more flimsy, right, given it's very open structure, but you can deform and do the same thing, measure, in this case, right, it's sensing ability or temperature response under different amount of strains that you can apply to this structure. So here, again, similar experimentally demonstrated, and also combined with the computation that shows you that you can actually, right, for a 2x2, you can twist this, and here panel A showing resistance change, or it can stretch it, or it can do this dynamic deformation, again showing you the similar response when you expand this to right, from that one linear channel to now more biaxial deformation. And you can actually use the computation to really show that this structure actually takes a lot of stress in the bridge component, whereas in the island itself is under very, very small strain. So that kind of showcases and helps us to understand the specific feature, which is, again, strain insensitivity, or this decoupled mechanical features to the electrical functionality. So if I go back to my initial argument on how do we use a structure to control properties of a material or device, here it's not quite coupled, it's actually completely decoupled, but you can see that really there is a benefit, or there is really power of start to bring in structural features into simple or to materials, or even to a device level that can help us to do things beyond what we normally would expect, right, from this type of material or structure material, to be more specific. So this is the one example I'm going to share, again, given this is much more real bulk scale devices, but that showcases really one of that concept. The remaining time, I think I have two more topics I want to discuss. One, first and second one is related to interfaces based on these 2D materials. The first example will be more about moly sulfide. And here we're going to look at the electrical interfaces between moly sulfide and separate material that we're going to introduce to enable a smart imaging capability, or neuromorphic imaging capability as an optical sensor. This work is in collaboration with Professor Taehyung Kim and Seoul National University. Actually, one of his students visited my laboratory. I think that's now already like 3-4 years ago, and we started for close to a year, and we started this discussion on can we create a photo-transistor that has a smartness to it, or in a very device level discussion, this will be a sensor, photo sensor combined with memory. But as like us, as human, our memory isn't forever, so we tend to forget things. So we wanted to create a sensor plus a leaky memory in a one combined system. So, and the question was, can we do that? And that was kind of the starting point, and then we started to think about the implications of these, and we call this neuromorphic photo-transistor sensors, and I'll briefly introduce the concept. It's actually pretty simple. So if you look at panel A, we try to really think about how we perceive things. So it's basically human vision. And if you look at how we learn or we start to perceive an image, it turns out our eye is exposed to multiple events of these images. Sometimes these images might be slightly faulty, but over time, you start to recognize that this is certain pattern. And the way we do that is we have essentially the pulses coming in. So these are the images that will happen in certain time repetition. Sometimes you see one time and you forget it. But if you see that event for many times, you start to remember that. So that's kind of what I'm trying to show you here. Short-term plasticity, long-term potentiation. So if you look at short-term plasticity, the optical pulses will generate some sort of electrical pulse, right? But it goes down to baseline quickly. But this is different when the pulses are very close together, right? So you see a pattern emerging. And what's different here is your overall current level goes up, right? So you start to recognize this is like a weighted sum, right? Summation over many pulses start to give you some thresholding event and start to give you memory that, right, tells us that, oh, I think I saw something I recognize from our past event. So this is essentially what's happening here in the schematic, and that's how we do it. And of course, human or our biological systems are even smarter. It has only one lens system. I think this is more optical side of argument. You don't even, right, like our traditional camera, I think we have more than 4 or 5 lenses there to correct for a number of aberrations. You do this with one lens, and right, you do it very smartly. So we try to mimic that. And really the core of this is this interface question I wanted to talk about briefly, but there are lots of very sophisticated fabrication, integration as well. And if you put this into a neuromorphic community, so what's the benefit? I think at the end of the day, right, if you look at what this is possible, is really hoping to save power consumption. I think that's really the critical element of neuromorphic imaging capability instead of a traditional sensor plus the neuromorphic circuit, for example, some sort of CPU and memory configuration. That's how we do things. And with the help of these memristor chips and memristor capabilities, that's really making these to be lower energy consumption, but still there is this gap in there, and we're seeing that our kind of ability is able to really make that so-called pre-processing component to be integrated completely to our sensor arrays. And so that's kind of the story that I'd like to tell you about. So let me go to the next slide. So the system is actually pretty simple. This is again, as I said, moly-sulfide as our channel. So it's a optical, right, optically active channel that's responsive to the visible spectrum. Depends on number of layers and things like that. You control different what's most sensitive photon energy to the channel. So that's the semiconductor. And what we added to moly-sulfide in this case is this organic layer. It's called PV3D3. It's a CVD compatible process, so you can actually deposit these very thin organic semiconductor with the CVD process on top of MOS2, so you can build this at a large scale, and you can configure your device with the metal gates and source drain contacts, and that's what you're seeing here in a cross-sectional view. But what's really unique about this compared to more traditionally widely used gate dielectric or aluminum oxide in our community that we learned was this PV3D3 enables a very nice long-term potentiation. So let me explain why that's the case and what we learned there. So we tested basically in panel D and E the features I explained early. So short-term plasticity, this is pretty simple. You expose light to your channel. You look at decay, and you can study, right, the decay time and things like that. So that's something. But now when it's illuminated by multiple pulses of light, so this is direct light pulses, and that's the current readout, you start to see when the light pulses are accumulating close to each other, you start to see the increase in overall current. And this is actually enabled by the photo response of this particular combinations of material. And you can see it in panel F. So let me try to explain it. So if you just take one kind of increase and decrease curve, right, under illumination, that's the shaded area here, you see that the PV3D3 respond in much more linear fashion here. So when the duration goes up, even with a single pulse, it goes up much more linear fashion. Whereas in aluminum oxide material, that's again kind of every material that everyone uses in our particular interface for moly-sulfide. you see that it saturates off after some time. So it basically gives us a very different photo response, and you can look at these decay times of this two stages in typical photo transistor, photo detector, whereas in our case, it can be simplified to basically just one linear term due to the I2 in this case is much, much larger than I1. So this is how we started off with, but then I1 goes away with the PB3B3 because the I1 itself is much, much smaller. So that's kind of summarizing here. But at the end of the day, really what this interface allows us to do is that we start to get this much more linearity in the exposure, time, exposure, power to its current that we're measuring at the end of the day. And that's how we learn things. That makes this learning process much more accumulative and without saturation. And that's right. That really is how human perceives over that repetition or over that time duration exposure. So here panel I really shows the difference, right? It's still not super like truly linear, but it keeps going up, whereas this more conventional interfaces start to saturate off. And we can ask the question why this is the case. So we turn to our theory collaborator at UIUC, and he showed us that actually it is this interfaces supporting of the band alignment between the MOS2 and PB3B3 being a type 2 band alignment. So you have basically an interlayer exciton-like state, so that can make these trap charges to be much more stable, and the accumulation of these trap charges are much more readily available compared to that of aluminum oxide, which has a type 1 characteristics, and the recombination is much more favored there. So there is a bit of this material interface support there, but from a device level, this is quite a nice feature to exploit to create these effect of long-term potentiation. So let me show you what we have done there in terms of additional demonstrations of these features, right, in the material from that material interfaces. Here I'm showing you one example. It's a 3x3 array, and if you look at panel A, I have, I think, 9 events here. We're trying to create a T, but as you can see, there's some error in each of 9 kind of exposures. So because of this error, right, if you just expose one perfect T for a long time, of course, the device will learn T. But if you start to have these errors in your image, now the device would like to learn what's been exposed the most common, right, throughout this 9 exposures. So that's what we're looking at. So from 0 second to up to 8 seconds of this exposure, and then once that the exposure is gone, you start to lose the memories. Although we accumulate it over that 8 seconds, it goes away over time. And you can also erase what's been stored by applying a negative voltage or the opposite polarity voltage to refresh the trap effect of this interface. So basically, you can create one event of this accumulated learning, and then once you extract that data, you can put that into another imaging this ability based on this type of devices. So I think we went a bit more. I think that this is what Daehyung is very good with. It's phenomenal in lots of these integration. So here is an example where this integrated system combined with this lens, with the arrays, with the integrated electronics in a single package. You can think of this as like a camera that's controlled by computers. And here again, I did show you that multiple faulty images that ended up training our sensor to learn pattern C, but we basically had about 30-something images that's exposed to the sensor with a single lens, and that allowed us to learn pattern C. You start to forget over time, and then get erased, and you can train a new set of images based on, again, this interface being really, I think, the driver for this particular work. Of course, there are lots of effort in making sure, right? If you think about the question, how do you make this to work with the lens? So it's non-trivial. That's why we, right? You have to think about lots of things because, right? Given the lens has a shape, you also need to shape your device array properly to have the right, the focusing and the aberration-free features, and you need additional electronics to extract data from each of these sensor arrays. So that's kind of the additional, I think, this integration effort. But at the end of the day, really, this rate, the simple star, really, I think, made it to the level that we have something that's functional as an integrated device. So that's kind of one example I wanted to share in terms of that electrical interface. My last example, most, I think, the recent work is about that mechanical interface. This is, again, kind of something that came about relatively unexpectedly, and I'll explain to you what we have observed here. Before that, I just want to show you what the basic intro to what I'm going to show you. So it's about fracture of a metal film. So this is a very common feature in lots of these flexible cables to some devices that were built on a soft substrate, being either polyimide or PDMS. When you apply strain that's above the fracture strain of the metal, you start to see these cracks on the surface. And these are from multiple literatures. It turns out these fractures, if you look at it, it's very much straight cracks. So this is like a mode 1 fracture. So if you think about this particular image, what we are doing is we're stretching it. So by stretching, applying an implant tension, you get fractures, right, along the y-axis. And of course, because you're stretching it, you get this compression. So you get these wrinkles, Poisson effect induced, or compression induced wrinkles. And this is very common. Same thing happens with the bending, right? The strain is large enough, you get similar fracture pattern. And now the question is, if you want to measure let's say this was your interconnect, and you're trying to measure the current from left to right, once you reach this fracture point, right, there's no path for electrons, right, for current to conduct. And as a result, this fails right away. So it's like, it looks like very brittle fracture. And electrically, it also behaves very much like a brittle failure, electrical fashion. So that's kind of the typical failure mode, from multiple substrate, multiple examples of metal on soft substrate. So in a mechanics community, people have been trying to use the understanding from nature, like Nakers, for example. There are lots of these structures that you found in nature that actually allows to create a crack deflection mechanism. And the way kind of nature does this is pretty, it's very, very clever. You basically have this layers of different mechanical properties stacked on top of each other. So basically you have stiff, strong, but soft, deformable kind of layers that are self-assembled by mineralization. And it turns out that interface, mechanical interface, is what actually causing the cracks. Let's say if you try to, if you have some impact on the lower side of the slab, then if you want the crack to not go straight, because if you go straight, it's a brittle failure. It fails immediately. It's something that we want to prevent. But by creating this interfaces, it is able to create in-plane, out-of-plane type of crack deflection. So this is kind of very, very widely accepted strategy. People 3D print these nowadays, so they can create this very interesting material. You can even create in-plane architecture to further guide the in-plane crack propagation on top of this out-of-plane engineering using the lamination. So that's kind of the knowledge that we know. So given these background knowledge that we were kind of familiar with before we get into this, but we were actually quite surprised to see this particular behavior. So this is I mean, I think this started maybe more than 4 years ago when Professor Pugh Kang was a postdoc in my laboratory, and we observed this in terms of electrical features, and I'll come back to mechanical discussions here. But what we were doing, what he was doing was to put a metal film on a flexible substrate such as PDMS. And here as the case, the schematic B shows, I mean, there are two cases that were compared electrically. One was the metal on substrate without, with a typical like chrome or titanium adhesion, and the other was the graphene was just underneath. Everything is the same, exactly the same. So this was kind of what, I mean, the two examples, and what we observed quite bizarrely. If I look at the resistance over strain, so this is not stress strain, this is a resistance strain, the bare metal versus the graphene metal, we start to see some sort of stable resistance region before it fell abruptly. So we have some sort of, in a mechanical term, ductility before this fails. But this is not a mechanical term, this is electrically characterized. So we thought this was quite interesting. And although at that time we weren't able to explain this at all, but we just saw something quite nice thing was happening. And my student came, Chase Cho came in, and he started to kind of study more of what's really happening. So we kind of go back to try to understand the mechanical behavior and then try to explain it, electrical, connect that to electrical observation. So, so fracture-wise, this is what we saw. Of the two examples, I'll show you more. Again, similar to what we know, the metal on just typical soft substrate, when you bend it above the failure strain, it basically fracture is very straight. Mode 1, type of mode 1 type of fracture mode. Whereas when you have to just layer graphene, you start to see very deflected, non-straight cracking behavior on the surface. So that's different, right? And the question is why, right? Because it's not like the 3D lamination that I show, it's just one layer. It must be something related to interface. And if you want me to show you more, so here are really the distinction between bare metal on soft substrate, bare metal with metal with the one layer graphene. What's interesting is with the bare metal, once you reach the failure strain, so-called these domain size or these small disconnected domains, they don't grow, they don't change, except for the distance between these domains will grow. So that's what you can see from these images. Whereas for the case you have just one layer, these domain size, not only the edges are very irregular, but their size gets smaller and smaller. So it looks like there's some, from just purely image point of view, there's some additional energy dissipation. So mechanically, this is still fracturing. It's still not completely failed. It's not done and you don't have anything. It's still fracturing into smaller pieces. And what's also interesting, and this is what we observed early on electrically, was if you start to add more layers, this happens, the failures start to delay even further. So 1 layer, 2 layer, 3 layer, 4 layer, it gives us very different distinctively different electrical responses. So that was also interesting. But here it's on the same substrate. I just want to show you copper. It's basically straight disconnection. 1 layer starts to see that, 2 layers start to see that. The domain size are different. So this is still larger than 1 layer. So this can further fracture. So this is not yet anywhere close to finished. This one maybe some halfway. Adding material that has even more impact. So the question, from just pure mechanics point of view, to us was why. So this is an interesting question. It took us some time to understand this, and our hypothesis, or I think our understanding, is like this. So it's a very interesting. So when you have this graphene underneath the metal, it turns out, so this is cross-sectional view image, you get a partial buckling of the film of a gold from the substrate of PDMS. And schematically, this is how we understand this. So if you have a buckle at a very top portion of this buckle, you start to exhibit much higher stress because it's not bonded to the substrate, it's being bent. And as a result, you start to guide that fracture crack to go through this buckle network, which is quite irregular. Right? If you see these buckles, they're never regular. They're actually a random process. And you have this multiple buckles. They're also competing depending on your load and depending on relative orientation between your buckles to the load direction. And then these buckles can also interact. So that crack guided by buckle will start to interact. So basically, you start to have this perturbation of fracture. And that's how we think it really leads to this, right? As you increase the strain, buckle interacts with the fracture and it delays it. You start to get this much more irregular features. That also is partly kind of responsible for connecting the current because it's not straight, it's not lengthening the gap, whereas your irregular shape, you have another irregular shape, you have a chance of also touching. So it's like a somewhat percolated type of electrical conductance type of model, but really that buckle initiated fracture connected with this irregular feature is what really uniquely allowed this electrical feature. So I just want to show you one image. You can see it already fractured to some degree, but these cracks are not completely happening in one shot. If you do the same experiment and take the same image, you actually see crack just goes right away. Speed of sound of a particular system. So that's not fast here. It's actually much slower and much more irregular. And the question is, what's the impact electrically? So I go back and then coming back, I only have I think 2 or 3 more slides. I'll finish soon. So here's the drastic difference. So it's the bare gold, that's a red curve, whereas this is a 4-layer graphing. I think that's the most drastic comparison. As you can see, this is in log scale. You see a flat regime where your resistance is same as you're almost same as your original resistance. So it's delta R over R0. So this is 1. So that's where you started, and you're there. So resistance almost seems as if it's locked until it shoots up. And by changing the number of layers, you get different responses accordingly, right? I mean, as I discussed, it basically shifts to be more strain tolerant. It works with twist, so that twist angle, right? It maintains up to 160 for 4 layers of fatigue. And I mean, you can ask this question: is it the conductive nature of graphene that makes this happening, or is it more than that? So it turns out this fracture surface actually is exhibited in MOS2, HDN. This is semiconductor. This is insulator. So of course, there are differences. It turns out graphene is most effective of the 3, but nonetheless, this fracture behavior, this kind of stable resistance behavior still persists in different 2D material that allows this basically buckle formation and guiding the crack formation, and of course its own intrinsic strength when it comes to stretching of the 2D material. And you can actually understand this, why this plateau, why this resistance stabilization happens by adopting a model kind of similar. It's not exactly that this kind of type of percolation type of model actually can fit this really well. And we were able to define something called electrical ductility parameter. When this parameter is high, you become much more electrically ductile. So basically, we're able to fit this stress strain curve, the resistance strain curve, similar to these power law type of behavior in the stress strain analogy. The last example, is you can ask the question: how do you compare this, in a true setting? And I think what really this might be useful for is if you measure the actual light luminescent ability as a device with this metal 2D interconnect integrated as instead of just a simple metal, you start to see that this luminescence actually go down as some sort of light emitting device gradually. So it doesn't go down right away. So you can set your reduction in luminescence as as if you're doing these structural kind of monitoring, right? You can set your failure at certain luminescent power, and then use that to predict or to at least understand where these interconnects are, and use that to replace or do the necessary maintenance. So that's really, so here it's showing you the difference. So on the left, and we made the substrate to be very, very thick. That's why just with side bending, it goes off in its luminescent power, whereas in our graphene underneath it basically remains very stable almost throughout this deformation. So I think that's it, what I have brought today. Hopefully this was of interest to you. I know, there's we don't do as much of a integration, but we try to come up with either a unique design or this understanding between how we can fabricate or design a structure or a property or capability that's beyond what's given to us. Really, that I think concept is still with the talk I gave just now. I think fundamental material level, there are actually even much more connections there. As I said, the length scale of things also matters a lot when it comes to some of the fundamental properties. So with that, I'll finish my presentation here, and thank you very much. And I'll be happy to take any questions or comments.
Right. Thank you, Dr. Nam. It was great and very interesting talk. I believe I learned a lot, especially about multiple materials. Now, I guess we have time for asking questions to the speaker. So you can either type your question in the chat box, or you can directly ask him by unmuting yourself.
I have a question, Professor.
Go ahead.
Hello, Professor Nam. Thank you so much for this very interesting talk. It's quite fascinating. I have a question that you're using 2D materials such as graphene for the interface for the device. Graphene is conductive. Why don't you use any insulating materials? Because since graphene is conductive, it might interfere with your device, right? I'm not sure. It might be a very stupid question. Sorry about that.
No. So, are you talking about this third topic, or
yes,
in general?
Yes, Professor.
Oh, so that's a very good question, and so let me tell you how we initially thought. So we thought when we saw this electrical behavior, we thought, well, there's island, the graphene might be a bridge, as you said. So graphene is helping with local electrical connection, and which still might be true. And I think for the interconnect, it probably doesn't matter anyway, because our goal is to conduct electricity or as a metal electrode. But just to respond to that point, we looked at, so it's a similar experiment or the same experiment, except for instead of graphene, we put moly sulfide in this example, which is semiconductor, and the resistance level of MOS2 is like much lower than gold. But I mean, so that's one, and you can also do hexabor nitride. This is complete insulator, then get a 6 electron volt. And we still see similar fracture surfaces of this irregular surfaces, and also this resistance behavior that I described. But if you look at, then what you can also do is, right, you look at so-called the strain, the failure strain here, and you can go to here. So this is graphene failure strain. This is MOS2. This is HBN. And you can compare them. It turns out graphene is better by, I forgot exactly, but by maybe, so we can, look at it. So this is, let's say 18%. So this is like 22, 23%, 24%. So you see the difference there. But nonetheless, they all behave a similar way. But graphene is better, and it's much easier to handle compared to HBN or MOS2, which the synthesis is not yet as close to that of graphene. So that could also be the differences in these, but nonetheless, the behavior still persists regardless of the nature of graphene or not.
Thank you so much, Professor.
Great. Dr. Nam, we have a question from Yoon-Sung Kim here. I don't know whether you can see that.
Yes, how do I
question.
see the chat box?
You can just click on top of it or let me read it.
Hi, Dr. Nam. Yeah, I can just say it here too. Yeah, thanks for the interesting talk. My question was regarding your graphene guided crack formation, right? So you showed us some the in-plane some crack formation or a behavior of the graphene layers when the cracks form. I was wondering whether you can generate some particular a larger scale pattern by incorporating some MEMS processes or photolithography, because from the pictures you've shown us, it seems like it's kind of it happens all over the substrate, right?
Right.
I'm curious whether you can create some unique patterns to create some unique, interesting, I don't know, some circuit functions and things like that.
Right. I think that's a very interesting question, and I think short answer is yes. I think, right, if you think about crack in traditional crack formation, you start from some sort of stress concentrator. So I think in like many, not many, but a few years ago, people have used that kind of notch type of predefined features, upper bending. You start to create these cracking, control cracking on these metals on soft substrates. So that's kind of well-established understanding. And I think in our case, the crack is dominated or guided by buckle. So if we want to create this crack behavior or control the crack behavior, we want to probably first try to control the buckle. And when we can control the buckling behavior, we probably can tie that to cracking. So as I said, it's possible, but we just need to think about slightly different way. Instead of indent, we create different features on substrate that could guide the buckling behavior. And yeah, of course, that could enable different crack formation in different sizes. I think to me, what's interesting is really, right, if you think about buckling, it's a competition, right? If one buckle form, another buckle form, when they're close enough, right, because they're kind of interacting already. So the density of buckle will be somewhat governed by, right, this relative competition. So is there a way maybe to control that further, right? So you can make it even more strain tolerant, right? Can you keep going, right? That's a fair question. And right, the way we did this here was by adding more layers that has an effect in formation of buckle networks. So that's one way, but is there any other in-plane patterning approach that can help us go there? That's an interesting question. We haven't tried anything in that, but that could be another control. If it can be done in a very low cost way, I think the industry might really adopt something like this, because they just need to add a layer of graphene, and that's all they need to do. So from that perspective, there's a way to do it very simple, easy, then there could be a nice way to do that.
Yeah, that's a good question and answer. I guess we have time for one more question from audience. Anybody else? Okay, if not, I do have one quick question.
Sure.
In the first part of your talk, you talked about Kirigami structure, and I saw that when stress is applied, it sort of had this outer plane buckling to observe that strain. And I'm just curious, once you make for example, for medical devices and others, we are stacking multiple layers for multi-sensor capabilities and others. But once you completely sandwich that Kirigami structure with additional layers, then what's going to be the limitation of stretchability compared to that open outer plane buckling case?
Right. So that's a great question. Actually, we did that experiment. So the simplest experiment we did was we put the Kirigami structure on PDMS or BHP. That's very sticky. So when you put it on, then the structure cannot buckle out of plane anymore. So if it's super sticky, then you are only limited to your in-plane. And that actually substantially reduces the stretchability because, right, you have this two bridges and you can do this in-plane, but you cannot do this. So that's how they stretch more. But this is gone. And that also brings back this gauge factor. So if you restrict completely the outer plane, the gauge factor comes in. So there's really, like stretchability wise, outer plane is very, very important. So there's a limited, I guess, operation regime if you restrict that mechanically, but electrically as well. So I think there is a challenge in terms of how are we going to package this, right? How are we going to, right? It's similar maybe in some sense, if I look back what Professor Rogers did, right? There was this this wrinkle structure to start with, and with the really the predefined adhesion, and then right, I think lots of recent work is really more on in-plane serpentine, but that allows some sort of out-of-plane deformation. If you completely get rid of that, then your gauge effect from the interconnect itself will kind of come in as a dramatic component to everything. So I think conceptually that's actually not too far off from what's been already established with this traditional PDMS with this serpentine in-plane stretching configuration. So that people can absolutely call it Kirigami, or just not being called that way. But that's kind of what we also learn in terms of how much outer plane you want. Of course, you don't want a whole lot, because otherwise, as a device, you're delaminating from the substrate that you're building, right, things onto. So I think there is that fine, fine aspects of how much of anything, of these things you want to add into your devices.
Got it. Yeah, I got that. Thanks for that. If there's no more question, then I think we can wrap up here. But in the chat box, I just typed Dr. Nam's email and his website. So if you have any additional interest, then please visit, or you can directly contact him through this email. Otherwise, I really appreciate Dr. Nam's time and great talk today again. And for audience, thanks for coming, and hope you have a safe holidays, Christmas, and also last of end of year. Thanks, everyone.
Thank you very much.
Thanks, everybody, for coming. Dr. Nam, I think Dr. Lee is here as well, and he said he has time to briefly talk.
Okay, yeah, sure.
Seminar. Can see his name. Oh, right there. Hi.
Yeah, I see his face. Yeah. Yes, I'll wait. Yeah, for people to. Yeah.
Yeah, I think we have a few minutes. Stop recording here.